Talking about the reverse bias conditions, we can say that in reverse bias, as we have seen the IV characteristic in reverse bias direction, that before Zener voltage or the knee current flowing, it behaves in the current diode. The current passing through the diode is a reverse saturation current, which is often in the order of 10 to the power minus 14 to 10 to the power minus 16. This range varies, and it could be minus 10 to the power minus 12 also. So do not take it fixed. And the reverse saturation current, as I have already talked about, it doubles for every 5 degrees Celsius. Reverse saturation current doubles for every 5 degrees Celsius, and reverse current doubles for every 10 degree rise in temperature. Now, moving on the other characteristics of the diode, one more thing I would like to tell you over this point of time, that the formula, how to calculate it. If you can see that if IC2, you need to calculate, okay, which is equals to IC1, that was the earlier, which is 2 to the power T2 minus 1 divided by this formula you can actually calculate the reverse saturation current. Now we talk about the other transition and other diffusion capacitance. These are the other parameters of the diode itself. In reverse bias condition, we have transition or depletion region, capacitance, and in forward bias region, we have diffusion or storage capacitance. In reverse bias, with the increase in voltage, the width of the depletion region increases. The depletion capacitance decreases. So remember, transition capacitance or depletion capacitance is in reverse bias condition, and diffusion capacitance, the majority carriers are diffusing into the other region, into N region, okay, or the majority carrier in P region are diffusing, okay, remember, are diffusing, they won't be diffusing, right? So let's just forget that. So in forward direction we have depletion or transition capacitance, and in forward direction we have storage and diffusion capacitance, and in reverse bias we have transition or depletion capacitance, okay. So moving on, in the reverse bias, with increase in voltage, the width of the depletion region increases. The depletion capacitance decreases because it is the formula that C is equals to epsilon of A, sorry about the A, divided by, sometimes my writing is crooked. So you can see that as the depletion region increases, the capacitance decreases, as the width of the capacitance is directly proportional to the voltage. Okay, this is directly proportional to the voltage because earlier we have seen that V square is equals to 1 by 2 Q by epsilon, okay, N E N D over plus N D W square, right? Okay, W square. So by this formula we know, oh sorry, this is not the square, remove this square. I have an eraser. Oh, it has erased everything. Oh, it will be raising everything. I'm not doing it again. So yeah, the voltage is equals to 1 over, is it voltage? Oh yes, it is voltage square is equal, this is not this, this is not square. Okay, now moving on. The reverse, so the capacitance is directly proportional to the applied voltage, as we have earlier seen from this from the formula, and it is V naught plus VR square, and the depletion capacitance is directly. directly proportional to the capacitance. So thus, kindly make few changes over in this line, that it's actually 1 over voltage, as the width of the capacitance is directly proportional to the applied voltage, which is root of V naught plus VR, and the depletion capacitance is indirectly proportional to the width of the capacitance. Thus, with increase in the reverse bias voltage, the width increases, however the capacitance decreases. Now, if one look at the reverse recovery time, which is Ts plus Tt, that is Tt is the transition time and Ts the storage time. Okay, that's the addition there. Looking in this figure, we can see that T is the storage time and Ts is the transition time. These are the two times. The total of these two is the reverse recovery time. Now moving on the load analysis. Start with the load analysis of the diode. If you apply Kirchhoff's law to this circuit, you will see that the external voltage is equals to Vd plus Id into R. The quiescent point is that point at which you will find the biasing point to be maximum and the most stable, okay, which is dependent on the diode voltage and diode current. Okay, remember these two equations. We have already talked about these two equations. Now look at one of the 2014 GATE examination question. Now it's telling us about the Schottky diode and a normal diode. You can see that both the diodes are connected in the forward direction, but you can say that one has a potential of 0.7 and other has 0.3. I've already given you the answer, but yeah, try to solve it by yourself, and you will find out that across the parallel junctions, you won't be having two different kind of voltage. We maintain a constant voltage in the parallel junction, one with the 0.7 and other with 0.3. With the one with the 0.3 will be first one to turn on. So providing a short circuit, all the current will pass through it and D1 will never get reached to its threshold voltage, and it will always remains open circuit. Now moving